Zenalux Biomedical has partnered with the Tissue Optical Spectroscopy Laboratory at Duke University to develop the Zenascope. The system is shown here. Today I'd like to run through a brief setup of the instrument and a demonstration of its capabilities. The Zenascope is an ultraviolet to visible wavelength range spectrometer that allows for quantitative optical spectroscopy in turbid media. The system uses standard spectroscopic hardware, proprietary software, and patented algorithms to provide information on biological tissue characteristics, or biomarkers. For the purpose of the demonstration today, I'm going to take measurements from my fingertip, and we're going to look at hemoglobin and how it changes once I apply a simple perturbation to my fingertip. I'm going to apply a rubber band to the base of my fingertip and take a look at hemoglobin saturation and how it changes over time based on that pressure. In order to start the system, you need to make a few simple connections. Here, I've already connected our fiber optic probe. The connections are simple. Simply match yellow to yellow on the probe and instrumentation, and then blue to blue on the other side. The next thing we need to do is make the power connections. I'll turn the instrument on its side in order to plug in the power and the USB cable. Here's the back of the system with the power connection and the USB cable. Let's turn it back to the front, and you can see two lights on the system. The blue light indicates that there's power going to the system. A second light will be illuminated once I initiate the software. To initiate the software, simply double-click on the preloaded shortcut on your desktop. Once you initiate the software, the instrumentation will go through a brief warm-up period, and you'll see a flashing green light illuminated. Once the light is steady, solid, you're able to start your experiment. This software is designed for the research user. We've designed the software such that you can enter pertinent information regarding your experiment. The first window that appears when you initiate the software is your username menu. You can either enter a new user or select from existing users. I'll select the default user. Hit OK once you have the correct username. The next window that pops up is your experiment tracking window. Here you can either select from existing experiments or enter a new experiment. There's also a note window where you can track your date, your samples, or any other pertinent information regarding your experiment. Once you've entered the necessary information, select OK. And then you'll be brought to the main software window. The first thing that you'll need to do is calibrate your system. Each system comes with a calibration standard that doubles as a probe holder. To calibrate the system, all you need to do is insert your probe into the calibration standard. Then you'll need to hit reflectance calibration. What appears is a diffuse reflectance spectrum of our calibration standard. You're looking for two things with your calibration measurement. First, you're looking for good signal. We know that we have good signal if our top peak is below 65,000 counts and above 13,000 counts. This is a great calibration measurement. The second thing that we're looking for is a smooth curve without sharp peaks. As you can see, we have a nice smooth curve. So we have good signal and very little noise. We're ready to take experimental measurements. So just hit confirm if you do like that spectrum. Now we're ready to go and show the demonstration. What I'm going to do is take the probe and just take measurements from my fingertip. To do that, Make sure the probe is flush with your sample, and then hit Run. A window will appear that will let you track your sample, your time points, and your sites. You can also enter information regarding your sample, such as anesthesia, temperature, or any other important comments. Once I've entered the information needed, I can go ahead and select Record Measurement. This will show the real-time data analysis. You can see that the software will show two plots. The top plot is our diffuse reflectance spectrum. The second plot that will appear is displaying the three quantitative endpoints. The endpoints that this software is equipped with are hemoglobin saturation, total hemoglobin concentration, and also mean scattering, which is reflective of cell density. Now our plot has appeared and all three parameters are on the same graph. They're color-coded and the key is shown in the right corner. The blue dot is our hemoglobin saturation. Yellow is total hemoglobin concentration, and red is mean scattering. What you can see is hemoglobin saturation is fairly high, hovering just above 70%. That's pretty normal. The hemoglobin saturation is measuring the oxygenation of all of the vasculature in my fingertip. That's the arteries and the veins. What I'd like to do now is apply the perturbation to the sample. I'll do that by using a rubber band to constrict the blood flow in and out of my fingertip. Then we'll take a series of measurements over time and see how hemoglobin saturation changes. To take additional measurements, simply hit Run and record measurement for each measurement. Wait until your second series of analyses appears before hitting Run again. And record measurement. Run. Record measurement. Now I'm going to release the pressure on my fingertip and take a few additional measurements. So let's take a look at our data. All the way over to the left, we have our baseline measurements. What you can see is that the baseline measurement for hemoglobin saturation is quite high. The next point is the point at which I applied pressure to the system. As you can see, there's a significant drop in hemoglobin saturation over time. Once I release the pressure on my fingertip, hemoglobin saturation increases significantly. This is as expected because once you apply pressure to your fingertip, the blood flow in and out of your finger is constricted. This means that your blood isn't able to replenish the oxygen supply in your tissue. And so you'd expect a significant drop once pressure is applied, and then you'd expect a significant increase once that pressure is released. What you'll also notice is that hemoglobin concentration started off fairly low, and once I applied pressure, it significantly increased. This is indicative of blood pooling in my fingertip. So the blood isn't able to release from the finger, and it's held and is pooling in the tissue. The third thing you'll notice is that scattering hasn't changed much. That's as expected because I haven't moved the probe from the site on my finger. The point of this demonstration is to show you the capabilities of the Zenascope. The Zenascope is a real-time, fast, quantitative diagnostic tool that is applicable to a number of health applications. This system is equipped with 3 endpoints: hemoglobin saturation, hemoglobin concentration, and then also scattering, which is indicative of cellular density and collagen content. We're able to tailor the system to any absorber of interest. This instrument is currently being used in a number of preclinical and clinical studies, including head and neck cancer diagnostics in the developing world, in the cervix, breast tumor margin assessment, and also in vivo breast biopsy.